So welcome everyone to the session on the contest. This year the contest was co-organized by the Center for Cybersecurity at NYU Abu Dhabi and NYU Tandon School, as well as Deltec and the Center for Hardware Security. So the motivation for this contest is basically that we see more and more threats are rising which directly affect the hardware. And we've also seen or heard about some of those challenges just in the prior session. And what we're really aiming at here with this kind of contest is to build up such related knowledge and experience in the CAD community in particular, because again we see that these kind of more and more emerging threats go together directly on the hardware, so the CAD community plays here a crucial role in order to address them in future CAD flows. The theme or the scope of the contest is then basically for the participants to devise and incorporate their techniques for designing more secure and trustworthy ICs. And specifically this year we had been looking into so-called hardware Trojan horses. And then the challenge or the objective for the participants was to harden the layouts at the design time against insertion of such hardware Trojan horses. And we'll talk about all this in a bit more detail in a minute. Just for logistics, what we'll do is in the first few minutes we'll talk about the background and some other details in the contest. And then in the second part we will introduce the teams, the rankings, and give some also insights there in the achievements of the participants, as well as finally the awards. A little bit of background on hardware Trojan horses. So first of all, we have to keep in mind the IC supply chain, which is nowadays obviously largely outsourced. So especially the fabrication then is outsourced, and this then may or may not be trusted from the perspective of the designer and the end user. So again, obviously this really depends on the assumptions on your thread model. But this is kind of the general idea for Trojan horses, as also illustrated here, just as indicated. Design is trusted, so illustrated in green. Fabrication is outsourced and not trusted. There could be some insertion of Trojan horses, and then this Trojan horse, or rather the circuit which has some Trojan horse in there, might pass testing as well. So, but also maybe we should say explicitly what is a Trojan horse. This is a malicious modification, could be either addition, subtraction, replacement of existing logic. There's really decades-long research already on this. What kind of Trojans are effective, what is possible in terms of digital analog Trojans, what is a good strategy to design them, what is a good way to hide them in terms of testing, to hinder detection of a Trojan during testing from the adversary point of view. The counterpart is there as well. How can we improve detection of Trojans either already at design time or later on in the field, and so on and so forth. So there's really a plethora of research here, which always is kind of fascinating people, this idea about some Trojan horse, really some modification in the circuit itself directly. Moving on. So moving on to the contest objectives, like already indicated, the teams would want to implement some physical design measures to proactively harden the layouts at design time already against this post-design insertion of Trojans. Obviously, the participants would want to also keep always the design quality and the design checks in mind, as well as PPA when developing their defense approaches. And there's also not a single right or wrong approach, because this is really a complex multi-objective problem, especially also with this more challenging technical setup what we have here this year. And now in the next few minutes, Mohammed will take over, co-organizer of this contest, to explain you more on those details for the technical setup.
All right, thanks for the introduction. I will now jump into more details about the contest. So for this year, we consider 6 different benchmarks, and all of them are crypto cores. As you can see here, there are a variety of sizes and complexities just to ensure different difficulty levels across the benchmark to the participant. We used Cadence tools both for the logical and physical implementation, and we used custom timing constraint for each benchmark. One thing should be noted here that we avoided optimization on purpose just to enable the participant to explore the trade-offs between the security and design metrics. Also, the vanilla script for both logical and physical synthesis was provided before the actual or official start of the contest, just to help the participant for better adaptation to the new library ASAP7 that we used for this year contest. But why this ASAP7 physical design kit and library? First of all, it is modern, so the node size is 7 nanometer. And we believe that it is likely the most detailed PDK developed by academia. It was originally developed by some teams from Arizona State and ARM. And there are a lot of files provided to just resemble a commercial PDK behavior. But along with this library, we also added some changes and modification to the library, like addition of color methods, or we introduced some max density rules, mainly to discourage the participant from adapting some simple solution to protect their layouts. And this replaced the NandGate 45 nanometer library we used in the previous contest last year. So in the benchmark release, we provided the post-root Verilog netlist and the def file, along with the design database and timing files. We also provided a list of cell assets for each individual benchmark. These cell assets represent the sensitive cells in each design, and they are selected manually from all flip-flops to represent the potential location like key registers that some Trojan could connect to for its trigger or payload. We also provided some reports for the evaluation and also the script for scoring and evaluation so that the participant could take advantages of using this script and evaluate the score on their own end. For anyone who are interested, this is the website. We will not delete these introduced benchmarks, and also the best results will be published there. Here you can see some examples for one of our benchmark, which is SHA-256. This benchmark was provided as a warm-up design before the alpha round to just help the participant get familiar with the new library and adapt to our rules, like density rules and some constraints that are newly introduced for this year contest. So on the leftmost image, you can see the placement cells, and the highlighted red one represents the cell assets for this design, while in the middle one, you can see the routing image. So all the metal layer here are represented in different colors. And on the right image, we can see the placement density map. So as you can see here in the corners, for example, there are lower dense parts, and in some parts in the middle, there are some hotspots or dense parts. But what we expect from the participant to follow in their implementation flow. For the floor planning, the participants are free to define the floor plan size and aspect ratio. So this is the only parameter that the participant can change, but other power distribution network planning, like the ring spacing, the offset, and the stripe-to-stripe distance are fixed, and the participant have to maintain the same strategy for the fairness. After that, we have the pin assignment. We expect all input pins to be located on the left side of the core, while the output pins are located on the right side. And for the power distribution network, we define some rules, and the participants shouldn't modify these strategies except for adjusting it to a smaller or larger floor plan. For example, the core ring must necessarily rotate in M6 and M7 layers, while the follow pins have to be rotated using M1 and M2. After this floor planning and power distribution network, the design has to be placed, and the clock tree synthesis should be performed, and finally the design is routed. So after performing all necessary checks and verification, participants are required to generate the def files and the post-route netlist for submissions. There are also some challenges like the DRC violations due to our modification to the library. So after routing, it is very likely that some violation occur due to different reasons. This is mainly intended to make it really challenging to achieve higher density. So as you can see on the left image, there is a DRC violation due to the pin access around this stripe. And if you move the cells a bit to the right and make some free space here, these DRC violation can be disappeared. So as you make the design more dense, you will face more DRC violation like these. Now let's move into metrics and the score. For the scoring, we evaluate the design based on their power, performance, and area, as well as the security. But since we have two different rounds in this year's contest, we evaluate the security in different manners. So for the alpha or the qualifying round, we evaluate the security based on the so-called first order metrics. So we calculate the regions or the gaps are of more than 20 continuous open placement sites, and also we count the free routing resources since the Trojan needs some routing resources to be connected to the original design. And for the final round, we extend these metrics with the actual Trojan insertion based on the engineering change order flow. So both security and PPI metrics are evaluated over the baseline to obtain the scoring for each submission from the participants. So this year we considered actual Trojan insertion for the final round, and there are 6 different Trojans per benchmark. Based on the triggering or the activation mechanism of the Trojan, there are 2 types. One is a combination of the assets chosen from a common layout region, and another one is the set of the assets that form a combination, which are chosen randomly across the design. Regarding the effect of the Trojan or the Trojan payload, we can have 3 types of the Trojan. One is the leaking Trojan, which is connected to the output of the cell assets to leak out some sensitive information, like the keys. The second type is the modifying Trojan, which flips the output of the assets. And the third type is the burn, which adds a redundant flip-flop change to consume more power. Here is an example of a Trojan with a 16-bit trigger and a 5-bit payload size. So on the left image, you can see the placement of all cells in the design, and the ones that are highlighted in red represent the additional Trojan circuitry. The bars on the right, you can see here on the top, it shows the corresponding timing slack before inserting the Trojan, while the bottom figure shows the paths after inserting the Trojan. As shown in this figure, you can see that the Trojan doesn't have a considerable impact on the timing, further hindering its detection. For the scoring, we mainly average the security and design scores for each submission, and since we have 2 different phases for this year's contest, we equally distributed the security points to the generic evaluation and the actual Trojan insertion. So for the generic evaluation, we consider the open placement sites and the free routing resources, while in the Trojan insertion, we define a score sheet in which the participant tried to achieve lower scores for better defense techniques. For example, if the Trojan insertion is succeed without any violation, their score would be something between 25 to 27. And if the Trojan insertion, for example, succeed but face some setup and hold violation, their score would be between 10 and 12. After calculation of these score sheet for each submission, the scores are normalized over 27, and they are averaged across different ECO modes, so the gap between the categories are intended. For the PPI or the design quality, we consider equal weights for the power, performance, and area. So for the power and area, we divide the scores or number from the submission by the baseline, and for the performance, we consider the worst negative slack for both setup and hold. We also introduced some constraints to make the contest more challenging and fair. For example, the participant cannot use the filler decap and tap cell to fill the layout. Also, one hard constraint is that the submission must meet the setup and hold timing checks, as well as having 0 DRC violations. And there are also some other constraints that the participant should maintain, like general IO pin placement or the functional equivalence. There are also some other restrictions. For example, the participant cannot delete the assets and use the custom cells. The metal layers cannot be revised, and each submission must include a clock tree. Finally, the participant must follow the PDN strategy provided in the reference flow. Thank you. This was the end of the part 1. I will now pass the presentation again to Johan for the interesting part. Johan, the floor is yours.
All right, thank you very much, Mohammed. Now we are moving to part 2. All right, so part 2 is about the teams, the achievements they made, and of course then the final rankings. So this year we had 14 registrations and 4 finalist teams only. Comparing this to last year, we will see that this year only 28% actually achieved the final rounds versus like 47% last year. So that means already here we can kind of see this year was more challenging. These are the finalist teams. And now we want to actually let them speak for themselves with some introduction video.
Hey guys, we are Team CU EDA. To start with, I'd like to share our beautiful campus. Then, here are our team members, and many thanks to our supervisor, Professor Evangeline Yang. The overview of our flow in this contest is shown here. We first shrink the floor plan as much as possible to give an initial layout by intervals. Then, logic cells are inserted into the nets with the highest timing budget. The design is placed and routed again with timing optimization. After that, buffers are inserted into large exploitable regions. And last, the positions of cells are adjusted in order to eliminate the exploitable regions. A sample layout is shown on the right, where the red cells are logic cells and blue ones are buffers. Thank you.
Hello everyone, this is Activity speaking. I'm Tong Xingyu. We are excited to share with you who we are, our journey in this year's ISPD contest, and our work about advanced security closure of physical layouts. This is the content outline of this video. First of all, a good news. Our beautiful campus has reopened. If you want to come by, we can share with you our personal invitation code, so don't forget to contact us. Then let me introduce our brilliant and hardworking team members. The handsome man on the left is our supervisor, Professor Chen Jianli, who has devoted decades in the EDA industry. On the right are our team members, sorted by expected graduation time. As you can see, our team is evolving and iterating in a fairly sustainable way. Yet it is the first time that we, a student team, participates in the contest. Unsurprisingly, we have faced lots of challenges, particularly in this industrial trade-off of conflicting objectives. Therefore, we would like to share our experience, our struggle towards a fairly acceptable score in this contest. As mentioned previously, this is an industrial multi-objective trade-off. That is to defend children attack with minimum design cost. We need to squeeze out continuous placement sites and available tracks, yet this will jeopardize the already unstable PPA balance. Since PPA accounts for half of the total score, we follow a natural strategy, that is to re-implement the designs to achieve good PPA, then deal with the children defense incrementally. There are some observations we would like to share with you about PPAs. First, from the graph above, we see obvious trade-off between power and setup WNS. Second, if area shrinks, a higher density more probably leads to outliers of the sum of power and performance score. So does the DRC violations. For more details, feel free to contact us at any time. As for the incremental children defense and exploitable regions, we use the technique of cell position refining and available site fitting. Note that the available site fitting is based on work of last year's winner. In short, these strategies manage to help in eliminating exploitable regions with minimum degradation in PPA. That's all for our sharing in this year's contest. Thanks for your attention. Once again, we are willing to keep in touch with the EDA community and is always open for communication. Thanks, y'all.
Hello everyone, we are Team NTHUTC Lab. We are all from National Tsinghua University, and we are happy to participate in this competition. There are 3 members in our team, which are Minfeng Si, Chunwei Chiu, and Chiasu O. Professor Tingqi Wang is our advisor. The current research direction of our lab is mainly divided into 2 main fields. The first, physical design automation in the field of ultra-large integrated circuit design. Second, adversarial attacks and defenses of deep learning networks in the field of artificial intelligence security. Here is the brief introduction to our methodologies. Firstly, we use parameter tuning to generate a layout with high PPA quality, as PPA is an important metric in this competition. After obtaining a legal layout, we then use dynamic programming techniques to minimize the exploitable regions in each cell row, in order to enhance the security of the chip. Thank you for listening.
All right, so thanks for the teams for sharing these videos. I think this was very nice to also, get to know them a little, and of course their hard work. Now, moving on in the presentation. So what we also did to actually get a better understanding of the experience for the teams is we did conduct a survey. And this year, we also did give the teams an option to remain anonymous so that they might feel more comfortable for really sharing also any critical comments in, let's say, the free text comments. And indeed, there were also comments on, let's say, different bugs. And this is truly appreciated, that we can have also these honest feedbacks. So different categories we asked for in the survey. First one was the experience with physical design. So there was average to little experience in physical design, which means, this is good, as in a lot to learn. For design closure, there was even less experience. That means working on post-layout design files. For hardware security, there was actually a large variation across the teams. And in general, there was less experience with Trojans. That is for both attacks, meaning insertion of Trojans, as well as defense against Trojans. So this is also good. A lot to learn basically here. In terms of scope, this was just fine for the teams. It was neither too difficult nor too easy. And then an interesting question was also what was perceived as the bigger challenge of the contest, physical design in general, or the security closure in particular. And somewhat surprisingly, the physical design was perceived as the bigger challenge. But then again, we could also argue that the contest challenge, that is really to make the layouts robust against Trojan insertion, goes actually closely together with physical design anyway. In that sense that a good defense will have to have a tightly optimized design and also a highly utilized design. And then if you're really pushing hard on the layouts in this ASAP7 PDK, this becomes challenging as well. And a bit more on this we'll also hear soon. And I guess this kind of explains these answers here. In terms of material discussion and feedback provided, this was rated as pretty good. In terms of the experience and outcome, this was rated actually a little less good. And the rating is here then, this is for the contest overall, and then the same rating we have seen for physical design. And again, this is probably reflecting on the challenges faced with the physical design. The outcome for the security closure is better, and I guess we can be happy with that. The timeline was perceived to be okay, actually a bit too short as well for some teams. And again, this is also helpful for us really to understand what was the experience from the teams. Now let's move on into the dynamics of the contest. So what we here see is the number of missions for only the finalist teams in the main phase of the final round. So that is the last 4 weeks of the contest. First, maybe a few remarks on the submission format and the logistics, since we didn't talk about this in the part 1. So the interface for the teams was a simple Google Drive. The teams could upload their design files and get some email notifications and results. That is the score reports, log files, design reports, the Trojan infested designs, and they got this all returned back into the drive. The backend was fully automated. That means there was an automated download from the drive. Initial checks were performed. The detailed evaluation was run using Innomus, a backup of all the results, and of course this upload was done. All the steps and procedures in the backend had been parallelized to have also faster turnaround time for the teams. But the teams had also been given actually the option to run the evaluation largely locally, since most of the scripts had been given to them, except for the ECO Trojan insertion. So for that, we didn't give the scripts, and we wanted to make here a realistic scenario, as in the teams don't know exactly what the Trojans are doing, and they also don't know exactly how they are inserted, but they do get back the GDS2 layouts with the Trojan-infested design. So then the teams could inspect the layouts and better understand what is going on and try to tune their defenses. So with all this background, let's go back to this plot here. So what we see here is then again the number of submissions for AES, which was the largest design in the contest with around 260K instances. All the other designs were much smaller with below 50K instances. What we can see now here is that the teams did rush for submissions towards the end, only in the last week for the contest. And we can also see that for some, but not for all the teams, there's a relatively large gap between the valid and the total submissions. So invalid, if you recall, that means basically a design fails in any of the checks, like for example, the PDN structure, or also for DRCs. And what we have seen is that probably DRCs had been the biggest challenge, also because we asked for 0 DRCs for a valid submission. And we can see then also that toward the end, the teams had pushed the layouts basically quite hard, so then many DRCs that came up. And in fact, there were also practical challenges, as in different tool versions would report different DRC issues. For example, at M1, there were different violations reported despite no signal routing there. And again, different behavior in different tool versions. So this was obviously a challenge. And in this scenario, this got identified by some team, and then we could also revise the evaluation and rerun the submissions. But still, this was a challenge, obviously. And again, the message here is that with this idea to hinder Trojan insertion, the teams had to push the layout really hard, and this really became a tough physical design problem. And then basically, we also see some limitations maybe of an academic PDK, and so on and so forth. So again, kudos really to the teams here with these achievements. Now looking into the submissions for SHA-256, this is a smaller design. Over time, we see here actually many more submissions. So you'll note here, this was actually more than 60 submissions from one team. And this makes sense because SHA-256 was the design used in the reference flow. So obviously the teams would explore SHA-256 throughout the contest. Let's look into a submission layout example for AES. What we see here is relatively dense routing as well as placement for this design. The utilization here is 90.21%, and this is without any physical or filler cells. So this is indeed impressive. If we're zooming in a little bit, so we see now here these kind of gap structures, which also Mohammed already indicated that we might have issues with DRCs for the pin access around the PDN straps. So that's why the teams also left some gaps in here. Now we look at the same zoom in, but you can notice here, basically, if I'm going back forth. So what we see here now are more gaps. And this is basically how the layout looks like once we prepared for the ECO Trojan insertion. Now the utilization dropped here to 88.28%. So this is still impressive, but you see we gained some room for Trojan insertion. And we did this basically through removal of buffers, downsizing, and so on, with little to no impact on timing. But we didn't do any more aggressive optimization means. And this was rather on purpose to keep it a bit more subtle, to not be overly aggressive for the Trojan insertion. For SHA-256, we can look at the same layout example. Again, dense routing, dense placement. Here, utilization is 93.78%. And again, also the slightly less dense layout once we prepare this for Trojan insertion with 90.34%. Now let's look a bit into the actual scores. So also as a remark here, we did share the intermediate scores with the teams. so that they could get an idea where they are standing during the cost nest. But we did only share with them the overall scores in order to not leak any hints via some of the more detailed metrics on more successful strategies by other teams. We also did not share such scores during the last few days of the contest to allow for some real competition again. Now going back here to this plot at hand, we'll start with the overall security score. And again, only for selected benchmarks here. We see that for AS, the teams did manage differently well. And this is also probably because it was the largest design and tackled rather late in the contest. For SHA-256, we can see that all the teams make very good progress over time. And it's becoming actually a very close competition, as you can see here in the very end. So again, good efforts really from everyone in the final round. Looking into a bit more details here, this is for the exploitable regions, this first order metric, what we already had been talking about. Again, also here for AS, there's a good progress, but no team actually achieved a perfect score here. And we might also notice here this local increase for the team C. So we have to keep in mind here that such kind of increases in the plots can be there because we're looking at the best overall solution. So that means if there's some increase here for this sub-metric, if you will, it must go together with some larger benefits or larger decrement for some other metric. So just to understand these plots a bit better. So this was for AES and for SHA-256, and actually also all the other smaller designs as well. Most, if not all, the teams managed then toward the end to achieve perfect scores. And I guess this is also understandable, given that the notion of exploitable regions is fairly simple to manage once you get a hang of, let's say, some buffer insertion or shifting of cells. The other part for the security was the ECO Trojan insertion. We see a similar picture here for AES. The teams did differently well, and also none did reach a perfect score here. Again, for the smaller design, SHA-256, teams did better. And also here again, the competition became quite close in the end. But also here, no team actually achieved the perfect scores. Perfect score, as in, the Trojan insertion would fail altogether for lack of space and resulting legalization errors for the Trojan insertion. So this didn't happen. But over time, actually, from, very successful Trojan insertion at our end with no violations at all, the teams managed to push hard back on these attacks, and they managed to induce DRC errors for a lot of the Trojan cases. So, and here we're actually facing the same challenges as the participants, right? So the same challenges with the dense layout and DRC issues we are seeing here as well. On purpose, we didn't really optimize further to get rid of these DRC violations. But again, so same challenges. And what we could say then is maybe that both sides actually remain successful. So we as attacker can still squeeze in the logic, but also the teams, you could say, are more successful because they enforced us as attacker to work on a layout where even any slight changes with a small Trojan will give rise to DRC issues. So again, good effort. And I guess the good thing is that there's still room for improvements and future work actually for both sides, attack as well as defense. Okay, so how does all the defense efforts look in terms of the cost? So for AES, again, we can see different approaches by the teams and some trade-offs. So there's indeed also for some teams some increase in the design cost. So for SHA-256, again, we would expect that the teams manage to optimize the designs at the same time. And again, remember also here that we didn't optimize the baseline layouts on purpose. So also this was kind of expected. We take a closer look into area, again, different approaches for AES. And for SHA-256, we see that all the teams managed to squeeze the layout to some degree. And this makes also sense from the defense perspective, because reducing the die outline would be an easy approach to reduce also the number of open sites. And also recall that we here report die area, not the standard cell area. So for power, for AES, we don't see really a big change here. For SHA, we see also again a reflection of the different approaches. And most teams were actually fine with some increment or increase of power as a side effect. And again, this can be expected if the teams, for example, would be employing buffer insertion to block or fill up exploitable regions. Timing, again, different approaches for AES, relatively large variance. And recall also here that we do consider both setup and hold slacks, and we do normalize over the baseline. And also recall that we reject any submission with a negative slack as invalid. Now, you might argue that anything with a positive slack is good enough, but we still did apply here the scaling for two reasons. One, to simply have some measure to judge between the teams, including their efforts or impacts on timing. But also the more subtle reason was to discourage teams from eating too much into the positive slack we have already established in the baseline layout. And this was done in order to facilitate the Trojan insertion, which might also need some additional timing slacks. But again, toward the end of the contest, we've seen actually that the issue for us as attackers was not so much the timing budget, but really then DRC violations as well. SHA-2 56, we see that all the teams managed to increase the positive slack further. So again, here's a close competition also between now basically two different groups of team. All right, so how does this look all together? So when we are looking into the overall scores, again, AES, not so much variation, but also here we can see this trend of stronger teams versus less stronger teams. For AES, for SHA as expected, then there would be this considerable progress really over time. And also here we see these two groups of teams and really a close competition there as well. All right, so let's look into the final scores. So this is what we have. These are the final scores. And since all the designs are different, we should not just average across the designs, but we would rather rank across, or rather, within the designs separately. And then we rank again to determine really the winners. So let's put the scores here to the side and let's look at the ranks. Now we have the corresponding ranks. Here we do compute the averages because we don't utilize further weights to differentiate, again, the different benchmarks. And what we see now here is we do have a relatively clear top team. We do also see that the last team does lag behind somewhat. And we also do see that there's still a pretty close competition between the teams 2 and 3, basically. And with these scores and rankings, let's come to the final part. Yeah, place 4, XD Security 2. Place 3, CU EDA. Place 2, NTHU TC Lab. And place 1, FDU EDA. So congrats really to all the finalists. And now let me wrap up. I think we're also running out of time slowly. So again, for us, the intention was really to continue building up experience and knowledge in the CAD community for this topic of hardware security. I believe, or we believe, the survey tells us this was quite successful. Again, really many congrats to the finalists. This was really great efforts from all. This were really tough physical design and security closure challenges. Thanks to everyone at ISPD committee as well as the community at large for having us. And please also keep in touch. We will update the website with the best results and some follow-up materials soon. And thanks again.